Okay, good morning and welcome up to microprocessor course. Today we're gonna finish lecture number 15. We talked about cache mapping techniques because we have the cache memory which is smaller than the main memory. That means that the blocks, all the blocks from the main memory cannot be loaded into the cache memory at the same time, at once. So we need to learn some cache mapping techniques, including the direct map, fully associative, and set way associative. So in today's class, we're going to continue with the write policy, cache write policy, because whenever there is any update into the cache memory, the data, the same copy of the data needs to be updated into the main memory as well to make sure that there is no inconsistent of the same data in the cache memory and the main memory. We have two different cache policy, write policy, including the write through and write back. So in today's class, we're gonna finish these cache write policies, then we can start with other internal memories. So before class, I'm gonna check on your attendance. Number one. 5, 1, 2, 3, 4, 5. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 17, 18, 19, 20, 20. Yuri, 20, 21, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 30. Peter. Classic number 1, 2, number 2. Willow. Number 3, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16, 17, 20, 21, 21, 22, 23, 24, 26, 27, 28, 29, 30, P21, classic number 15. Okay, good. So we're gonna start today's class. Now, before continuing with cache writing policy, I do just have to remind you that we have the central processing unit, which does incorporate the registers, and then we have the cache memory, which stands between the central processing unit and the main memory to avoid multiple accesses to the main memory, as we have seen that there is a disparity when it comes to the speed between the central processing unit and the main memory. Thus, the cache memory is to contain or to hold most recently accessed data, main memory, to avoid multiple access to the main memory. Thus, this will improve the memory speed. As a result, it does have a significant positive impact on computer performance. So this is the cache memory. And if you still remember, depending on the technology, we have different levels of cache memory. We have level 1, we have level 2, etc. We have level 1. And typically, level 2 is larger than level 1 when it comes to the size, and it is slower. Level n is typically larger than level n minus 1, and it is typically larger. So it is there. The cache memory is there to combine the high speed of the expensive memory system, but which are very expensive, and low speed but large memory system with less price. So this is the role of the cache memory. Last class we talked about the cache replacement algorithm, because we have more blocks than we can load into the cache memory. That means we have the cache which has to be full, and when the cache is full, the system needed to use some cache replacement techniques to replace existing blocks into the cache memory with new ones. Now, the next problem is when the same data into the cache memory needed to be updated, either in the cache memory and we have the same copy in the main memory. What happened? What are the procedures? How the system does handle the inconsistent between the same copy of the data which is in the cache memory and the data which is in the main memory. So we have to talk about the cache write policies and coherence issues. Now, cache block replacements, we have different cases. If the cache block was not modified, or it has been overwritten without writing to the main memory, or if the block was modified, that means write to, but the write back to the main memory before the replacement. That is one. So they have, we have some key challenges, including multiple devices, let's say input-output devices that needed to get access to the memory. And if the cache is updated, but the memory isn't updated for the same copy of the data, that means the main memory is invalid because it holds the data which is not updated. Or if the input-output devices updated the memory and the cache is not updated about the same copy of the data, that means we have the cache memory which becomes invalid for the same copy of the data. Now, for multiple processors, we talked about multi-core mania. In modern computer system, we have seen that they came up with the idea of having many cores onto the same computer chip. That means we can have a write on one cache. So we have a computer system which includes different cores. This is core number 1, and this core 1 has cache memory, let's say level 1 cache, and we have core number 2, and it has its own level 1 cache. Then we have core number 3, which has its own level 1 cache. Then this is the central processing unit, and we have these cores which share the same level 2 cache. Let's say we have a level 2 cache, and we have level 2 cache. Now imagine if there is any update into the level 1 cache, that means the update of the data is not being made into other cores of the same central processing unit. That means a write in one cache may invalidate the same data in other cache. So these are the key challenges in cache memory. For example, we see that if we have multiple devices and there is access to the memory, then if the cache is not updated, but the memory only, the main memory is the one which is updated, that means we have the cache which becomes invalid. Or if we have the input-output which updates only the main memory, that means that we have the cache memory which becomes invalid. Now, multiple processors. In the case of multiple processors, each processor has its own cache, and if a write is done only in one cache memory, that means this may invalidate the same data in other cache memory. Now, what are the write policies that need to be applied? We have two types of write policies, write back and write through. But before we talk about this write policy, we needed to understand that the cache memory is smaller and faster to store the most recently used data, as I have said before. So it acts as a buffer between the central processing unit and the main memory to speed up the access. Now, write hits. If the address is in the cache, we have seen that this data will be returned to the central processing unit, and this is a hit. Now, this is faster than returning the data from the main memory. So there are some issues, data inconsistency. That means if there is only update in cache memory and the update is not taken into consideration in main memory, that means the data, the same copy of the data in the cache memory and in the main memory, they are not the same. So we have these two solutions, write through and write back. Now, let's talk about the first one, write through. For write through, that means that the writes go to both cache memory and main memory. That means we have the cache memory that needed to be updated at the same time as the main memory is updated. So we have write through policy, write through policy, cache memory and main memory updated at the same time. Cache memory, memory, and main memory updated. Now, that means the main memory is always valid. So it is much easier. It is consistency across all the processors. I mean, in case of multiple processors, we have all the processors which are updated with the same copy of the data. Now we have high memory traffic. This is one of the drawbacks of the write-through policy. We have high memory traffic. That means because the system needed to update the main memory and the cache memory, that means we have what we call bottleneck problem. The next one is write back. The write back. For write back, it does update only cache memory. Updates only cache memory. So that means there is a data bit that needs to mark the modified block. Here is the modified block. So means that the main memory will be updated when a data block is replaced. So the main memory will be updated a bit later after the block is about to be replaced. So this will reduce the main memory traffic which was faced by the first write policy that we call the write policy. So we have the main memory that might be invalid, and it is more complex for the hardware implementation because potential bottleneck. All right, so we needed to have some example for the write true. We have the write true on the screen. Here we have the V to indicate that the cache line is valid. Then we have the tag field to indicate the address. Then we have the data. We have the main memory which has the same data. And after the write true, that means we have the main memory and the cache memory which have been updated for the same data. Now you can check easily that after the write true, we have both cache memory and the main memory which are all updated for the same copy of the data. This is write true. Now, the write true needed to update both main memory and the cache memory at the same time. So it is simple and it is reliable. It is very simple, it is also reliable because it does update both data, both main memory and the cache memory. But it is suitable when write operations are not frequent to avoid high traffic memory. So it has to ensure data consistency and helps in recovery when there are some issues, let's say the power failure. So this write policy can help to recover because it keeps the main memory and the cache memory all up to date. So this means the first one, the write true, is simple and reliable. Simple. Now, we have high memory traffic for the write true because the system needed to update both cache memory and the main memory at the same time. Now, we're going to talk about the write back. The write back. You see, we have, before the write back, we have the cache memory, which has this data at this index, and we have the valid bit, which is set to 1 to indicate that we have a valid data in this cache line. Then we have here the main memory with this address, and it contains the same copy of the data as the cache memory. And after the write back, you see we have the cache memory which has been updated with a new copy of the data, but you see that the main memory here is still having the previous data. That means that the cache memory has been updated, but the main memory is outdated. That means this is a kind of gap for this write policy because it does only update the main memory when the block is about to be replaced. So we see now we have the write back again. We have the valid bit, and we have the tag, and we have the data. The main memory and the cache memory have the same data. After the write policy, you see that we have the cache memory which is up to date, and we have the main memory which is outdated because it still have the previous data, but you see the cache memory has been updated. But when the cache line is about to be replaced, that is the time the data will be updated into the cache memory. Though we have the main memory which is now updated because this cache line is about to be replaced. So this is how the write back works. That means updates only cache memory, and the main memory will be updated when the cache line is about to be replaced. Now we have the write back update only data in cache memory, and the main memory will be updated when the cache line is about to be replaced. So it has to use the following replacement policies, including the list recently used, all the FIFO. We have a data bit to indicate whether a block was modified, all not clean. Only when the data block are written back to the memory, and this we have to reduce the number of memory write operations. So modified data may be lost on cache when there is a system fail. That means there is a high probability to lose the data because we only have the cache memory which is up to date. That means if there is any system issue which can affect the cache memory, there is a high probability for the system to not contain the data because the data is only in the cache memory. So write mishandling, we have to talk about the write allocated or write allowance. Now, for write miss policy on cache miss during write, we have write allocated. That means the block needed to be fetched from the cache memory. Then it has to perform the write. No write allocate, that means the system needed to write immediately to the main memory, not into the cache memory. So does not have to load the block into the cache memory. This is for no write allocate. That means the write operation is done immediately to the main memory, and there is no need to load the same block of the data into the cache memory. But for the write allocate, we have to fetch the block into the cache memory, then perform the write. So typically we have 15% of the write, and it's about the HPC workload, and it is about also 33% for vector-to-vector multiplication. Now, up to 50% is about matrix transposition. This is very highly likely to be happen, especially when you are dealing with image processing. Now, this is the key differences between the write through and the write back. We have the write location, the cache memory, and main memory update at the same time for write through. We have the write back. Only the cache memory is up to date. Then the main memory will be updated when the block is about to be replaced. For the speed or performance, the write through is slower because the system needed to update both cache memory and the main memory at the same time. Then for the write back is faster because the main memory will be updated a bit later. So for data consistency, we have high data consistency into write through mechanism because the data is up to date in both cache memory and main memory. Implementation, we have the write through, which is simple, and we have the write back, which is a bit more complex. Now we have a simple example of the Intel 86 cache organization. The processor call consists of 4 major components. We talked about the fetch and the decode, which fetch the instructions and the decode the instruction. And we see that we have the level 2 cache, where the system needed to fetch instruction. And we have the decoder to decode those instructions to help the microprocessor understand what it has to accomplish. Then we have the execution unit, which executed the instruction that has been fetched by the BIU, as we talked. Now we have the Pentium 4 blocks. This is a kind of more modern central processing unit. As you can see, we have the load address unit, and we have the store address unit. We have the simple integer arithmetic logic unit, and we have more complex integer arithmetic units to accomplish more complex arithmetic and logic operations. And then we have integer registers filed to store some data. This is a register memory. Then we have the L1 instruction cache, which is 112K. This is the level 1 cache to store the instruction, as you can see. Then we have the decode and the fetch unit to fetch the instruction from level 3 cache. As you can see here, we have level 3 cache, which is 1 megabyte, and we have the level 2 cache, and we have the level 1 cache data. And you see that this is the one of the modern central processing unit, which include all these components that we just talked. So mainly, this image that is shared on this screen is a block of diagram of a central processing unit, which include the pipeline with the cache memory hierarchy. So this is typically a supercomputer, which include the central processing unit pipeline with multiple arithmetic logic units, load and store units, and 3 levels of cache to improve execution throughput. So this is an example of modern central processing unit with the pipeline technique, which can help them to execute multiple instructions in the same clock cycle, as we discussed last time. Now, we have the Pentium 4 cache operating mode. We have the Pentium 4 cache operating mode. We have the level 1 data cache is controlled by 2 bits in one of the registers, which are labeled CD, means cache is disabled, and we have NW to mean that there is no write-through bit, and there are 4 Pentium instructions that can be used to control the data into the cache. So we have the cache which is disabled, and we have here no write. And if we have these 2 combinations, that means we have the cache fields, which is enabled, and the write through, which is also enabled. And that means invalidate is also enabled. When we have the cache disabled, which is on, and no write, that means we have the cache fields, which are disabled, and we have the write part through, which is enabled, and then we have the invalidate, which is also enabled. So if we have both cache disabled and no write, which are all set to 1, we have the cache fields and the write through as well as invalidate, which are all disabled. Now, we're going to talk about the cache performance model again. So cache timing analysis use the following terminology. We're going to consider the TCT, which is the time to compare address tag with the cache line tag. That means, if you still remember, for example, the direct mapping techniques include the address, which does contain the tag line number to select a specific line into the cache memory. Then we have the offset field, which allows the system to select a byte or a word within a block. Now we have the TCT, which is the time to compare the address tag with the cache line. Then we have the TRL, the time to read a cache, time to read, time to compare, and this is the time to transmit a byte or a word to the processor. And we have T-hit, this is the time that the system spends on a cache hit, and we have the T-miss, which is the time the system spends on a cache miss. Now we have for direct mapped cache mapping techniques, we have to check the tag field against the line is tag. That means we have the tag field from the address from the central processing unit that needs to be checked against the line is tag, that is the cache line is tag, and we have a miss operation when the operation is ended. Then we have a hit when there is a read of the data block from the cache line, and it has to fetch a word or a byte using the offset field, as I said. The tag is for addressing purpose, and the line number is to indicate the line number into the cache memory, and we have the offset, which helps us to select the byte or the word within a specific block into the cache memory. Then we have the timing that can be expressed with the following equation. We have T-hit, that is the time the system spends to return the data when we have the data into the cache memory. We have the time that the system it takes to read the data, then plus the time that it takes the system to compare the data. That means it has to check if the tag field from the central processing unit is addressed against the line tag, plus the time that it has to use to compare the tag field against the line is tag. Now, if there is a miss, that means the data is not available into the cache line. We have the time miss. How much time does the system, it takes the system to retrieve the data when it isn't into the cache memory. We have the time to read the data plus the time it takes to compare the tag field with the content into the main memory, because the system needed to expand its state in the next level of the memory hierarchy. Now, we have the direct mapped with more advantages, which because it is simple and it has a faster speculation. Once the address is computed, that means there are the possibility that the cache line is known, and the cache line can be read while the tag is being checked. So there is a probability that the cache line can be read when the tag is being checked. So this we have to have the processor to use the data before confirming the cache match. There is a high probability for the processor to use the data before the system confirms about the tag match. Then we have checking and fetching, which can be done in parallel, which can be done at the same time. So we have checking the tag and fetching of the data, which can be done at the same time for direct mapped, because the system knows about the tag that needs to be checked with the line number. And the system also knows about the line into the cache memory. That means the checking can be done and the fetching also can be done at the same time when the system is still doing the matching, the checking between the tag from the central processing unit and the tag, the cache line is tag. Now we have to talk about a fully associative. The line number is unknown until tag comparison is finished. If you still remember, for the fully associative, we only have the tag and the offset. That means the system isn't aware about the line number until we have the system is not aware about the line number until the comparison between the tags is done. We have the tag and we have here the offset. The system does not provide the information about the line number. The line number will be non-associative, that is 2. The line number will be known until when the tag comparison is done. So we have a hit time which matches that of a direct map. We see that we have the hit time which include the lead time and the transit time, as well as the time that the system it takes to compare the tag from the address from the central processing unit, and the line number is tag. Then we have the miss time, which depends only on the tag comparison. So we have, for fully associative, we have the same hit time as the direct map, but the miss time is totally different because it only takes into account comparison time. It takes only into account the comparison time. We have the TR, the time to read. Then we have the time to transmit data. Then we have the time to compare the tag from the central processing unit and the line from the line number. The line cache line is tag. Then we have T-miss, which is only equals to the time that the system used to compare the tag from the central processing unit and the tag, the line number, the cache line number is tag. Next, we have set associative. For set associative cache, we have the system cannot transmit the byte and compare the tag at the same time, like the direct map with speculation. So we have a circuitry which allows loading data blocks from all the lines in a set. So data is being transmitted only after the tag check is done. Now we have seen that for the direct map, the checking and the fetching can be done at the same time. The system can return the data for the line number before the tag comparison is done, which can improve the system speed. Now, for set associative, data is transmitted only once the tag check is already completed. So the timing equations reflect this sequential process. If the set associative is augmented with a way prediction, that means there is the following equations that need to be held. We have the T hit, the time that it takes the system to return the data if we have the data in the cache memory. That takes into account the time for reading the data, the time for transmitting the data, and the time that it does take to compare. That is 1 minus FP times TCP. Well, FP is the fraction of time that the way prediction succeeds. Now, we have the set associative cache with the way prediction. If the FP is equals to 1, that means we have the set associative which behaves like a direct map. So it becomes a one-way set associative, which is a direct map. And if it's equals to 0, it does behave like a set associative cache without way prediction, which is the worst scenario. So we just finished with the cache performance model, and here we do have a summary of the cache performance model for the direct map with speculation, which does not take into account the time for target comparison. The hit time is equal to the time it takes the system to read the data plus the time it takes to transmit the data, because we have seen that the checking and the fetching can be done at the same time for direct map with speculation. We have fully associative cache performance model. Here it is. And we have the set way associative. Here it is. And we have the set way with way prediction. If here we have the FP which is equals to 1, that means we have the one-way set associative, which is the direct map. Now, for designing option to improve the cache performance, we have to minimize the mean time that it takes the system to retrieve the data. If you still remember, we had this expression for two-level memory. Then we have the probability of taking a path times the duration that it takes the system to return the data from the path. Then we have the summation of all the probabilities in the path times the summation of all the times in the path. So what is the probability of the data to be found in this specific memory level, and how long does it take the system to return the data if it is available in the specific memory hierarchy? So this is the mean time to access data in a memory hierarchy. We have learned about this expression for a two-level memory system, and we went through a general form of this for a multi-level memory system. We have the TS, the minimum time, which is equal to the hit time, times the T1, that is the time the system spends to return the data when it is available in the cache memory. Then what is the probability to find the data in the next level of the memory, and how long does it take, and so on and so forth. Then we have the simple expression, which is H1 times the time it takes the system to return the data, plus 1 minus H1 times the T penalty, the penalty time. Well, the penalty time is the mean time to access data if it is a miss at level M1. Now we have cache performance improvement techniques. So the way prediction, what does this do? What is its importance? For the way prediction, it does slow down the hit time. It does slow down the hit time. For cache capacity, for example, if you have smaller cache, that means we have a very faster cache. So it does reduce the hit time. When it comes to the line size, as you can see, it has importance on the time, the hit time. And for the larger line size, this can reduce the miss rate. When it comes to the cache associativity, this, for example, the direct map with speculation, we have lower hit time. For fully associative, this has a very important advantage on the time, hit time. It has a very important advantage on the hit time. Then we have more flexibility for replacement quality, which can reduce the hit time in the lower level of the memory highlight. So this is your 5-minute break. Take your break. We're gonna resume class after break.